So the next speaker is Valentina Candiani from the University of Genoa, and she's talking about radiomics and artificial intelligence for stratification of meningioma patients, a clinical study with MRI data. So,
well done.
The stage is yours.
Okay. Okay. So good afternoon, everyone, and thanks to the organizers for giving me the opportunity to talk here today. Today I'm going to talk about an ongoing project that I have, that we have been working on for some months now, together with Cama, that you have heard before, Cristina Campi and Piana from the Department of Mathematics, and actually 2 subgroups of the Department of Mathematics at the University of Genoa, and 3 neuroradiologists from the San Martino Hospital in Genoa, Rebella, Martino, Resaz, and Luca. I thought about this talk as a little bit of a continuation of Isabella's previous talk, and I'll explain you why in the next few slides. So my talk today will follow this outline. I will first give you a little bit of an introduction for those who weren't here before to listen to Isabella about radiomics and the general settings that are present in current literature. I will then shortly present the graphical user interfaces that we have developed for image segmentation, and then I will dive into the actual results and the clinical analysis part. So, as you have heard before, radiomics is a methodology that is used for extracting quantitative information from medical images. So what usually happens is that in oncological applications, we have some neuroradiologist that looks at the images and say, yes, there's a tumor, it's in the frontal lobe, and it should be operated. But they actually get these quantitative values or quantitative information from other examinations. So, for instance, histological exams, blood samples, urine samples, or like everything else. Instead, we would like to extract some quantitative information directly from the images, and more specifically, we would like to understand some things about spatial distribution of signal intensities in the image, or pixel interrelationships within the tumor region. And the long-term aim would be to enhance clinical decision-making in the sense that we would like to somehow link the quantitative feature extracted from the tumor lesion to these biomarkers. More in short term, we would like to understand if this is doable. And specifically, we would like to understand if there is even a correlation between this biological and histological information and the features that we extract. Needless to say, the advantages of these techniques are quite obvious in the sense that it's non-invasive and it would actually replace histological exams. It's not expensive and relatively fast because one just needs to get the images through our pipeline and extract those data. On the other hand, challenges make a huge part of the problem because, as Isabella already talked about, we need to understand the robustness of the feature extraction procedure and the reliability of such features. And then, well, I will talk about this a little bit more in the next slides. So this is the general workflow that is currently used in literature. This is not something that we have invented, but it's something that we based our pipeline on. It's made of 4 steps. First one is image acquisition. That doesn't really depend on us because that's the physician work with all the problems that come with it. Second step is image segmentation. So we need a stable algorithm to extract, to at least isolate the tumoral lesion. Third step is what Isa talked about, so feature extraction. About this, let me say that features can be divided somehow into different groups. We have shape features that can be size of the tumor, shape, eccentricity, and so on. We have first-order statistics features such as mean, standard deviation, contrast-based values. But then the biggest part of the features are represented by texture features. And these are, for instance, count of path in the image with the same count of pixel with the same gray levels, or zone in the matrix with the same gray levels and so on, so texture features. Last step is data analysis, and in this talk I will briefly talk about image segmentation and then a little bit more about fourth step with the clinical analysis. More specifically about the fourth step, what we would like to have, we would like to get a stratification, which is just a fancy medical term to mean classification, of patients diagnosed with meningioma according to two different tumor biomarkers. One is tumor grade, that can be stadium 1, 2, or 3, and the second one is the so-called PD-L1. And I'm not going into detail here, but you just need to know that it can be classified as positive or negative, so binary, and it gives some sort of assessment of on the aggressiveness of the tumor, but that's just positive or negative. And the tools that we have used so far, or that we plan to use, are clustering techniques to classify the patients and to assess the most informative features among this big set of 44 features. We have performed statistical tests to quantify the classification reliability, and we are planning, or at least I did it 3 days ago, some tests with neural network for prediction. So, but step number 2, we have implemented 2 graphical user interfaces. This is the first one. With the first one, codes are on GitHub. With the first one, one can browse the magnetic resonance images, and this is completely 2-dimensional. So even if we get 3-dimensional volumes of data, there's just stacked images, stacked B-dimensional images. One can also insert suitable region of interest, like this green rectangle, around the tumor. And then all the functionalities on the right-hand side are needed once the segmentation has been done to modify it a little bit, maybe delete some region of interest or merge the part, and, well, functionalities that we found useful once we have done the work. And the second graphical user interface is useful to check the segmentation results compared to the MR image, modify manually by dragging all the dots like she presented before, one by one. That took some time. If the segmentation, of course, is not as we would like. And then finally launch Radiomics computation. And the 2 different options refer to, this is the completely automatic level set, well, active contour level set method for segmentation. And the second option is something that we added, and it's related to some continuity criteria between the slices. So if the segmentation on one slice is significantly different from the previous or the next slice, then this option replaces the segmentation at this stage with either the previous or the next one. And this, well, speed up a little bit the process. So, point is, we end up with 47 because they're 3-dimensionals, while the 44 before, well, I'm not going into detail, but here we have 47 features for each patient. So there are quite many, but there are some dimensionality reduction algorithm to at least understand what to do with these 47 features. And then about clinical analysis. So let me present a little bit the data set that the doctors were able to provide us with. We have 34 meningioma patients, so not as many as one would aim at, but that's what we have so far. And here I just put some examples of them, because the data set was quite heterogeneous. We have patients with one tumor district, which is well defined compared to the background. But we also have patients with one tumor that at some point on the final slice is split into 2 connected components. But we also have patients with 2 tumors that have to be classified differently. and then with 2 connected components. So we included all these cases in the pipeline. So the aim would be to classify these images according to these 2 biomarkers. And let's have a look at the first one. This is tumor grade. Here we have classification with respect to just tumor grade 1 and 2, because grade 3 is actually quite rare. On the left-hand side, we have a 2-dimensional representation of the k-mean clustering results on the first 2 principal components of this set of features. So y-axis is the first component, and then x-axis is the second principal component. Patients are colored by by groups, so group 1 is grade 1 and group 2 is grade 2. On the right-hand side, however, we have the principal component representation once again, and then the degree of contribution that each feature gives to the principal component. So for instance, correlation gives quite a great contribution to principal component 1, while for instance, dissimilarity is more on principal component 2. Some comments. If we look at this plot, we cannot say we are really satisfied with the results, because the best case scenario would be to have 2 clusters, very well defined, well separated. This is not the case, and the reasons might be different. First of all, the small data set that we have. It was also quite unbalanced, because we had, I think, twice as many patients with tumor grade 1 and then just a few with tumor grade 2. We've computed some tests to see which feature actually classified them best, and turns out that the best one was coarseness, which is a texture feature. But if we look at the violin plot of this feature, one can notice that it's not absolutely informative, because once again, the best case scenario would be to have one, let's say, grade 2 violin plot at the, let's say, bottom of the graph, and then the other one really at the top of the graph, so that the mean are clearly different and the classification has some sort of meaning. Well, we're still waiting for new data to come, and we're also doing some tests to see whether there are some problems. But this is the situation right now. A little bit better was the classification with respect to PDL1. It's not as good as one might aim for, because we don't have 2 different clusters, but we can see some sort of structure. Here maybe some parabola or something that we could, some parabola along which the patients align, or at least that's the aim. We haven't tried it yet with this type of classification, but that's one thing to try. And in this case, the best feature, the most significant feature was this GLN, gray level non-uniformity, one because that's a special case, and the second one was eccentricity, but once again, you cannot really see much difference here. So we're still in the process. Once again, some discussion. Good thing is that the features that we classified as consistent and more reliable in our 2-dimensional analysis, so in the work that Isa presented before, are actually the best in separating the patient groups. So there is some sort of reason behind, and there is some sort of reassurance in that. About clinical findings, we're still in the process, but specifically the classification according to PDL1 was better than the one according to the grade. Why? That's something that we should investigate with the physicians. And once again, we could try out some higher degree classifiers, or maybe some half-transformed technique for the second case. Finally, just a few things about challenges. Well, we've encountered many in our work. First of all, they're quite getting real data is a long process, and that's one thing. Also, what the physicians give us is something that is completely messy, and the pre-processing part takes some time in data homogenization and gray-level quantizations, which are fundamental steps in the feature extraction procedure. And then this is something that we came up with, the curse of dimensionality. We usually get these very horizontal data sets with lots of features, but then a very small population, so not really helpful in the statistics analysis. And finally, what we talked about already, also another problem is standardization, because data should be acquired with the same magnetic resonance scanner, same contrast agent, and same technique, same sequence, and so on. And this is something that, well, we should take care. But I mean, we're not really. That doesn't really depend on us. And then, of course, need for standardized protocol in image acquisition, in feature extraction. And there's some initiative already, but it's not quite there yet. Finally, just some further studies. I said upcoming shortly in a hopeful way. We would like to integrate this new data that should arrive soon, stratification with more advanced tools. This is something that we should be able to do in a short time, in the sense that this is just same patients, same pictures, but with a different acquisition sequence. And then some stratification with respect to another biomarker, and these are data that just arrived. And in the long run, well, maybe apply this pipeline and this clinical analysis to other situations like multiple myeloma. And then if you have other ideas, just please let me know. So thank you.
Thank you, Valentina. And there are some questions from the audience. Oh, yeah.
Thank you for your presentation. Just one question. If I understood correctly, you want to classify into two classes your data, and you have a lot of features, but a few examples.
Yes.
Why did you try with something tailored for these cases, like, for example, super vector machines that maybe can help? Is in your future plans or not? Because neural network suffers the lack of data.
Yeah.
So,
Yeah, it's something that we could. It's something that we can totally try out. We haven't, but yeah, it took some time to get to this stage, just managing all the data and implementing the pipeline and the graphical user interface. But yeah, sure, that can be done, and I'll keep it in mind.
thank you.
Another question?
Yeah. I have a question. You mentioned that you would use neural network approach for projection.
Yeah, I didn't really expand on that. I have tried out just to see if something came out of it. So by splitting the 34 patients in like 20 and 14, well, it didn't really work out that well. I implemented just an easy, fully connected neural network with just one hidden layer. But that's a start. I mean, really 3 days ago. But maybe with more data, it would work out a little bit more.
Yeah, the
reliably.
session with this neural network, because it has specifications, so you can experiment and play around.
Yeah, exactly.
Hidden layers and hidden
yeah,
layers.
exactly. I need to try out all these, all different settings, and yeah, maybe with more data. Yes.
Yeah.
So, but yeah, something that can be done. Sure.
Okay. Some other question? Thank you again, Valentina.